Welcome to the Teja Statistics. In this lecture, we are going to discuss about the unbiasedness estimator. So, an estimator expected value of t n is said to be uh, an unbiased estimator of theta if it satisfies expected value of tn is equals to theta for all small n belongs to the capital N. Theta of is a parameter. So in last lecture we discussed all these things, the definition. Let me explain one problem or theorem. We can say that the proofs to understanding about the uh, theory of estimation in that criteria of the good estimator. So in that unbiasedness property we are discussing, and we are going to see some problems on that. This the sample mean x bar is an unbiased estimator of the population mean mu. In this example, what we have to show that this x expected value of this x bar equals to the mu. Let x1, x2, x3 and so on xn be a random sample drawn from a normal population with mean mu and variance sigma square. So xi follows the capital N value, that is mu comma sigma square. So consider here the x bar is equals to 1 divided by summation xi. So apply expectation on both sides and you will get the expected value of x bar. So if you apply 1 by n is a constant, and the expectation won't be applied here, and this will be added over here, that is expected value of x1 plus expected value of x2 plus and so on expected value of xn. These are all the random samples from the normal populations, so hence we can write mu, so which we can easily say that mu1 mu2 and so on mu n summation mu I. So where xi, x1, x2, x3 and so on xi or xn are the IID random variables, identically independent random variables. So nn gets cancelled, you will get the mu value. So here the sample mean x bar is an unbiased estimator of the population mean which from the normal distribution. Let's see some more examples and the problems. Like let xib follows a binomial of n comma b, then x bar is an unbiased estimator of the population mean np. Let x1, x2, x3 and so on be a random sample. Here you can see the x bar is an unbiased estimator of n comma p. Here our estimator is x bar and the value is here the parameter value is np. Let x1, x2, x3 and so on be a random sample drawn from a binomial distribution, then with the mean that is n comma p and the variance is npq. Now we have to consider the tn value as that x bar, 1 divided by n summation xi. Similarly apply the expectation over here, then you will get expected value of 1 divided by n of summation of xi, 1 divided by n summation expected value of xi. So this will be 1 divided by n summation n into p, because expected value of xi value is n into p. 1 divided by n into n of np, that is nn gets cancelled, expected value of x bar equals to np we got. So here therefore x bar is an unbiased estimator of np. Next coming to the point, that is the third question. We have to prove for the Poisson distribution also. If xi follows the Poisson distribution with the parameter lambda, then the sample mean x bar is an unbiased estimator of lambda. Proof: let x1, x2, x3 and so on xn be a random samples drawn from the Poisson distribution. So expected value of xi is equals to this lambda, and variance of xi is also be the lambda. Now consider the sample mean x bar is equals to 1 divided by n summation xi, and apply the expectation over here, then you will get the same 1 divided by n be the constant, and summation the expected value of xi. So what is an expected value of xi? That is lambda from the Poisson distribution, and if you remove the summation, then you will get the small n gets cancelled, and here lambda, expected value of x bar is the lambda. Therefore the sample mean x bar is an unbiased estimator of the population parameter, theta value, that is lambda. Next, the sample is not an unbiased estimator of the population variance sigma square, but s square is equals to 1 divided by n summation I runs from 1 to n xi minus x bar is an unbiased estimator of the population variance, which is denoted by the sigma square. Proof: we know that s square is equals to 1 divided by n summation I runs from 1 to n xi minus x bar whole square. So you can write the s square formula like this also. If you apply the expectation over here, then you will get the expected value of s square equals to 1 divided by n summation I runs from 1 to n. So expected value of xi whole square minus expected value of x bar whole square. Then you will get the another formula, that is v of x is equals to expected value of x square minus e of x whole square. Here you can see by replacing x by xi, then variance of xi is equals to expected value of xi square minus e of xi whole square. From that expected value of x square we got, so that is variance of xi is equals to variance value if you substituted as sigma square, and the expected value of xi is equals to sigma square, that is plus mu square. So from by replacing x by x bar, then you will get variance of y bar of x bar is equals to sigma square divided by n plus mu square, which is very important and easy to understand. Substituting all those values and 2 and 3 in 1, then you will get e of s square. So expected value of s square value, that is 1 divided by n and n into sigma square minus sigma square divided by n, like that. Sigma square 1 by 1 minus 1 by n, that will be the n minus 1 divided by n. So that is equation number 2. So the expected value of s square is equals to sigma square. So it is not at all equal. So sample variance is a biased estimator of the population variance. From star we have expected value of s square is equals to sigma square of n minus 1 divided by n, multiply with n divided by n minus 1 on both sides. Then this will become n minus 1 of n minus 1 divided by n of n divided by n minus 1. On calculating this, we can say that so expected value of s square will become sigma square. Okay, the sample variance is an unbiased estimator of population variance. Okay, similarly you can do this for uh, if x1 x2 x3 and so on xn is a random samples drawn from a normal population with respect to the then show that t equals to 1 divided by n summation I runs from 1 to n xi square is an unbiased estimator to mu square plus 1. Yeah, this is your homework problem. You can solve it by your own. Okay, so thank you.